Hello and welcome to the STEMCstudio channel. Mastering units of measure is a very necessary part of any physics student's education. And using a computational modeling tool that is able to handle units of measure can be a very effective way of achieving that mastery. The reason for this is that the student can approach the process of carrying through units, as we call it, in a calculation in a very non-threatening way. They can build in the units into the calculation, have the computer do the calculation, and they can see if the results come out right, or the computer can tell them there are incompatibilities in the calculation. So that's a very non-threatening, very powerful way to learn units of measure. So what we're going to do in the video today is we're going to review what STEMCstudio has to offer in terms of units of measure calculations. And then we're going to look at sort of the bigger picture of when would you want to use units of measure, when might you not want to use units of measure, what options have you got for building your own units of measure versus using some off-the-shelf units of measure that are provided. Okay, let's get started. So I'm going to reset this project. I'm going to keep this project because it's got documentation that I want to have, but I'm just going to sort of reset it by deleting a whole bunch of stuff here. Bear with me one moment. And so we've essentially got ourselves down to the beginning of a project, a brand new vanilla project. The only difference is that if you want to use units of measure, you need to bring in, and you want to not build your own, you need to bring in a library that has them. And the library that I recommend is one called davinci-newton. And the latest version of that is currently 101. So we're going to bring that in. Davinci-newton contains a number of geometric algebra numbers. And these numbers are written for various dimensionalities of problems. So for example, there's a 1 spatial dimension geometric number. There's a 2 spatial dimension for working in the plane. There's a 3 spatial dimension for working in 3 space. And there are even some space-time numbers for working with one space dimension, 1 time dimension, and then there's one for working in 2 space dimensions and 1 time dimension. So the first thing is you have to decide, what am I doing in my problem here? What's the dimensionality that I need to solve this problem? Let's just say that for some reason you are looking to solve a problem which is a 3-dimensional problem. So an appropriate number that we want to import would be, and I'll just show you how you first reference the library. So you say, I want to import something from davinci-newton, which is the name of the library, and I hit Control Spacebar, and you can see all of the things that you can possibly import. Well, what we're looking for is something which is called either Geometric 1, Geometric 2, or Geometric 3. Geometric 3 happens to be the 3D geometric number that we need. Now, if you're not familiar with geometric numbers or geometric algebra, you could go and visit my course, my Geometric Algebra first course, and learn about them there. So basically they are, if you like, what the simplest way of thinking about them is they're like a union of all of the different kinds of numbers that you might want in 3 dimensions. So for example, they can represent points or scalars, they can represent vectors, they can represent bivectors, which are like rotating objects, and they even have volume elements. But if you don't want to go for that complexity just right now, just think of them as they are, say, vectors with components x, y, z, but they also are like the union with a scalar which has a component a, which is the scalar value. So in this case, Geometric 3 has an A component, X, Y, Z component, and then it has these other planar components, and then finally a B component to represent the volume. Okay, so we bring it in, and maybe the demonstration will demystify it a little bit. Geometric 3 has a number of constants on it, and so, oops, So I might want to create local copies of those constants, like kg is just a sort of shortcut to a kilogram. And what we can do now is we could say print line. So we're going to use our print function that we've got below, and we're going to say, okay, a kilogram equals, and let's just take a look at what kg is. Okay, so kilogram equals 1 kilogram. So the first thing you'll observe is that the way that units are sort of offered to you is that there isn't a sort of special unit class that you need to work with. The units are actually part of the geometric number, the measure that you're dealing with, right? So this is like a measure, and these are like, this is like a unit of measure. Okay, so this makes it particularly easy to actually work with them. So we can have, for example, a meter. So m is a meter. Oops, I need to put geometric 3 there. Let's go and take a look at that guy. So a meter. Now, whether you want to use m as a shortcut, it might conflict with other things, but that's your choice. Okay, and then let's say do a second. So we're going through the at least like the 4 very common units that you have in the SI unit system, which are the kilogram, the meter, the second. Let's just do the second now. So we got 1 second, and the final one, depending upon how you like to think here, is to do with electromagnetism and to do with the electric charge, or if you like, electric current. So you can either use the Coulomb, or if you prefer, you can use the ampere. So it's up to you to decide, which one is appropriate. I think in modern units, people actually kind of prefer the ampere to the Coulomb. I think it actually kind of like it creates a better standard or something like that. So even though we think of them as related through time, of course, an ampere being a Coulomb per second, the way that they're actually measured is one's more fundamental in a sense than the other, and I think the ampere now is considered to be the more fundamental. Okay, so let's call that a Coulomb. Okay, so that's just an example of, we'll put in, just for completeness, I'll put in the ampere here. You can decide which one you want to use. They obviously only differ by the time amount. Okay, so there are your units of measures, and then to use these, you basically multiply them out. So, for example, I can create a velocity, and that might have units of meters per second, right? So this is meters per second, and you can see it's calculated over on the right here. You can see it's calculated m over s equals m divided by s. Now, of course, the way that you're supposed to use this is that you can sort of naturally say, okay, my velocity, const v, equals 5 times a meter divided by a second. And so I can then just print out my velocity, right? And then you might want to do something like, okay, I want to compute a mass, so const. Oh, before I go on with that, let's just stop there. What I've given you is not really a velocity, of course, it's a speed. And so this is a good opportunity for us to actually talk about the different elements in these geometric numbers. So for example, in geometric 3, we have the basis vectors E1, E2, and E3 corresponding to the X, Y, and Z axes. So I can I'm just going to set up some local constants of that. This is just, for these, it's just convenience to do this. E2, E3. And so I can say 5 meters per second in the E1 direction, for example. Or I might do something like this. I might say 5 in the E1 direction plus 3 in the E2 direction meters per second. Okay, so there we go, 5E1 plus 3E2 meters per second. So that's my velocity. Okay, and then, you can kind of like do calculations. I could do, say, mass. So I could say const m, my mass equals 5 kilograms. And let's just print that out. Now I noticed that, oh, you noticed got some problems because I'm reusing my m. So I'll use a big M for this. And let's take a look at m. So m is 5 kilograms. So now I can compute the kinetic energy, for example. So let's print the kinetic energy is equal to 1/2 times m times, and then we will have v squared, so v times v. Okay, and you'll notice actually that the units library in STEMCstudio, or rather coming from davinci-newton, recognizes the pattern, which is energy, and says, okay, this is 85 joules, or because there's sometimes situations where you're kind of looking for like the work, so it's the force times the distance moved in the direction of the force, you may want to see that as Newton meters. Okay, so that's really all there is to it. Very, very simple. I think we've kind of like covered everything about sort of using them. We've created scalars like mass, we've created the velocity vector, and as I said, you can go ahead and create a whole bunch of other geometric elements in your space, but that requires some knowledge of geometric algebra. Okay, let's take a look at the README because I've made a few notes here that I think might be useful. The first thing is some caveats, some pros and cons. When I first started doing units of measures, I was working with some physics teachers, and we were kind of like gung-ho about doing it. Got to put these units of measures in, so everywhere we do a calculation, the units kind of like get carried through. I've sort of backed off a little bit from that position. I think that obviously mastering units of measure is vital for the physics, for the scientist, but we can kind of achieve that mastery at the beginning, and then perhaps going forward we use the shortcuts that expert physicists use. Like, for example, once we become expert, we say, okay, if I do a calculation, I just put everything into SI units, and I don't bother carrying through the units because I know at the end I'm going to get the right units. That makes sense with pencil and paper. You can do a little bit better when you have a computational modeling tool like STEMCstudio, because carrying through the units is kind of effortless. Okay, that's one side of so a pro side of putting units into your simulations and to the projects that students do, and that kind of thing, is they get to practice the units of measures, and it's a very non-threatening way to learn. If they get the units of measure wrong, the slips will be caught, and you will see either the result will be wrong, like you'll get a manifestly wrong answer, or perhaps some intermediate calculation will throw an error because you're trying to add incompatible units. Okay, so you're trying to add a kilogram to a second or something like that. Okay, on the other hand, using standard units of measures can have some downsides. One is, if you're using SI units, you can really get into some scaling issues which could actually obscure the fundamental physics. So for this reason, like for example, if you're doing special relativity, it really makes sense to use the speed of light equals 1. I mean, if you're kind of carrying through your units in in units of C, standard C meters per second units, then you are going to be dealing with all sorts of strange kind of like numbers, large numbers, and all sorts of things like that, and it will obscure the physics. I think another thing that I've experienced is that when you're building simulations, getting the units right can actually be an impediment to kind of like getting the basic physics equations right. And so I might suggest to you, at least something to try, is to build your simulations without units first, and then maybe add the units later, and make sure that you can consistently add through the units. But I think at a certain point in the physicist training, we sort of forget about the units. The units are just kind of like just for doing the real world calculations, but for understanding the physics, we sort of drop them. Let's just talk about some of the features. Well, I've already demonstrated that the davinci-newton units can recognize certain patterns in units. So for example, it can recognize energy, it can recognize magnetic fields, volts, things like that, things that occur in electrostatics. So there's some useful stuff that happens that by using the library. And something else that happens is if you're carrying through units in your computation, the library davinci-newton can actually do that quite efficiently by caching various intermediate unit calculations so that you don't proliferate a whole ton of unit objects, and which could kind of become a problem for a simulation if it's running for a long period of time. Okay, just now a bit more background information that you might find useful. Implementing units is not specific to STEMCstudio. The units are not burned into STEMCstudio itself. The units come entirely from the library. The power comes from the davinci-newton library. So that's just something that you should know. We're not burning in the units. If you want to define your own units, you could write your own units classes, and I'll give you some hints as to how you might do that later on. STEMCstudio does support operator overloading, so you can see here that you can just do very natural kind of syntax for using units of measure within a measure. But you don't have to use operator overloading. You can turn off operator overloading, and incidentally, this is how you do it. You uncheck it there. And if you turn it off here, then you have to just then use the methods on the geometric class. So for example, I mean, it gets a little bit kind of messy because you're going to E1 dot, and then you start doing things like, multiply by a number 5, and then you can start chaining these together, and then add E2 dot multiplied by the number 3, and then you want to multiply the whole thing by a meter, and then you want to divide it by a second. So this is the alternative if you don't have operator overloading on. Let's just see if we can make this work here. So we'll turn that off. We'll let's carry it through. Let's do a kilogram dot multiplied by 5. Okay. And yeah, there's a problem. Multiplication, straightforward multiplication expects a geometric number, so I've got to go multiply by number. Okay, should be good. And yep, here it's painful too. So m dot multiplied by number, oops, big M dot multiplied by the number half dot multiply by v and dot multiply by v again. So you can see here the power of operator overloading. Let's just check it works. Kinetic energy 85 joules, yeah. So you can do it that way. Obviously, operator overloading has sort of great benefits. Maybe pedagogically, I don't know, but certainly you can read the code a little easier. Okay, what geometric measures do you have available to you right now in davinci-newton? Well, this is what we currently have. We've got standard Euclidean measures for three-dimensional space, that's geometric 3. For two-dimensional space, or the plane, that's geometric 2. And not very interesting is the line, but sometimes your problems are actually one-dimensional, and really it's kind of redundant to be carrying through extra quantities in that case. So it is possible to use geometric 1 in many cases. And then we have the space-time versions, which are obviously non-Euclidean. They are sort of Minkowski, if you like, space. So we have, in the case of space-time 1, we have one space dimension, one time dimension. And in the case of space-time 2, we have two space dimensions and one time dimension. And all of these support optional units of measure. Okay, now if you actually want to understand a little bit more about how to use these with, beyond what I've said, there is documentation for davinci-newton. If you go to the project settings here and you go over to this description, you can click on the link. That's generally true for any of these things. And you can see that davinci-newton has documentation. So for example, for geometric 2, right, it has documentation for that class, pretty extensive sort of class. So that can be very useful, and it also allows you to sort of go down to the code. So, let's sort of find this. So, you can actually kind of like peek into the code and understand kind of like what's happening under the cover. Sometimes that's more valuable than the actual documentation itself, just to know what really is happening. Okay, so let's go back. And then finally, what happens if you want to implement your own units of measure? Well, we can discuss whether that's a valuable thing to do. But basically, the approach in davinci-newton is that we sort of build off a class called QQ, which represents rational numbers. And obviously, when you're doing units of measure, multiplying units is really like adding the rational exponents, right? So that's why this is a sort of a foundational class. The class dimensions then contains 7 of these rational numbers corresponding to the 7 SI. I think they're really kind of called dimensions in that case. So obviously we've got mass, length, time, which are and electric charge or electric current. And then you have the 3 other sort of, to me, rather obscure ones, like the candela, the measure of sort of luminosity, the measure of amount. I think that's the mole, and there's another one which I can't remember. Let's go and look. So we'll come back to here. Go look for dimensions. There's dimensions, and we got length, mass, electric charge, time, and we got amount, intensity, and temperature, thermodynamic temperature. So essentially you got the Kelvin, you've got the intensity, which is here, I'll just drive in here. Okay, it's not very specific here. Maybe in unit it's more specific. And then you got amount of substance. Okay. Yeah, in the dimensions, it's actually not specific to SI. It's actually just these are dimension quantities. And then the dimension quantity is kind of wrapped in something called unit, which is where we bring in SI units. And we've got a number of constants in that unit class that correspond to sort of common units. Let's see. Anyway, we've got candela is one of those kind of like obscure ones. We've got amount, so we should have mole somewhere. There we go. We've got mole. And what was the other one? Kelvin, right? There's the Kelvin. Okay. So the other ones are all kind of compound units and things like that. and they're just here for convenience. Obviously, you can build all of these other units out of the basic 7 SI units. So in terms of reusing this, you could certainly reuse the unit, and you could use that in, say, your own vector class or geometric number class. And to get some ideas of how to do that, you can just kind of like consult, say, the geometric number here, and just see how that is used. So we go to the constructor. We can see here how the unit of measure is like an optional thing that's added, and it gets made to be a property of the class, and it gets carried through in the calculations and that kind of thing. Okay, so you can see this is how it checks compatibility of units. So that's one way you could use it. The other thing you could do is you could write your own, right from scratch. You could write your own rational numbers. You could assemble those into certain dimensions, and then you could kind of like create the SI variants of it or whatever. I think that's probably a less useful exercise from a physics point of view. It's more like the kinds of thing that you might want to do from a programming exercise standpoint, and maybe one day I'll write a video about how to actually write a rational number that you can use in STEMCstudio with all the operator overloading and, say, the greatest common divisor function in it to simplify the rational number down. But I think my suggestion is, when you want to use these units, I would say go and use the geometric measures, learn what geometric algebra is all about. It doesn't take that long, and then just use them this way. Obviously with the operator overloading. Yeah, that's about it. Okay, so that was a little whirlwind tour of using units in your geometric simulations or whatever simulations. And there are many examples in STEMCstudio. If you click the examples button, that will take you to simulations where the units have been fully carried through. And it's an interesting exercise to do that, and not to just use dimensionless units. So there are plenty of other places you can kind of like go and look at examples. Okay, that is it. I am going to carry on. So that's units and measures. I hope this was useful to you. If you like this video, give me some likes just to let me know that I should be carrying on with this, or if there's something that you'd like to see changed, please add a comment below. And finally, if you would like to see more videos about STEMCstudio in general, subscribe to the STEMCstudio channel. Okay, take care. Happy coding. Goodbye now.